All right, here's section 3.12, combustion analysis. Now, combustion analysis is a technique, and that's a technique that you can utilize to determine how much carbon and how much hydrogen is in a solution or in a substance. And the way that you do it is by burning it in the presence of O2. And essentially what you're utilizing is the knowledge that a hydrocarbon plus, so I'm just going to write HC for a hydrocarbon, plus O2 in the presence of heat is going to produce CO2 plus H2O. Okay, so you're using that as your foundation. Okay, so combustion analysis is a lab technique that is used to determine the empirical formula of compounds containing carbon, hydrogen, and perhaps oxygen. A known mass of a sample is going to react with oxygen. All of the carbon in that sample is going to end up as CO2. All of the hydrogen ends up as H2O. So you'll be able to determine the mass of CO2 and relate that back to the mass of carbon that was in your original sample. You'll determine the mass of H2O and be able to relate that back to the original mass of hydrogen in that sample. So you'll have those two components and be able to say something about, well, what is the overall, or based on the mass of the original sample, here's the mass of carbon and hydrogen in each of those. All right, so this is basically a combustion analysis apparatus. What you have is your sample right here. And you're going to have this in a combustion chamber. And that combustion chamber, you are going to flow a stream of oxygen. You're also going to have a heating element in there in order to help that subject or that sample burn up. Okay, so what's going to result from that is you're going to have the products of H2O, CO2, and O2, because remember you're adding excess O2 in your original sample. Now, you're going to have an absorbent substance that's going to absorb all the H2O that's produced. So H2O is going to be collected, and you're going to determine how much H2O is there. In addition to that, you'll have kind of a second chamber. So the first chamber would be your H2O, kind of, I guess, capturer. And your second chamber here is going to be for capturing CO2. And then O2 is going to flow off and release from there. So you have these two chambers that are going to collect the H2O and CO2 respectively. Now, you can determine the mass of the carbon and hydrogen in that sample based on, well, dimensional analysis. You'll be able to say the mass of the CO2 that we have in our absorbent substance, we can relate that to the mass of carbon dioxide, or the molar mass of carbon dioxide, then say, well, we know that 1 mole of CO2 has 1 mole of carbon. 1 mole of carbon has a mass of 12.011 grams. Therefore, the mass of carbon that was present is this. You do the exact same thing with the mass of H2O. I think the best way to get after this is really to look at a specific example. Here's the flow chart for what you're doing, but again, we're going to look at a specific example. And this might be worth your while to go ahead and revisit this periodically, but here we go. So this question at hand gives us 2.50 grams of butyl butyrate. This contains carbon, hydrogen, and oxygen. We're given this information that it has a molar mass of 144.21 grams per mole. When this was burned, we got 6.10 grams of CO2, 2.50 grams of H2O, and from the combustion analysis. The question, though, is asking what is the mass of oxygen in this sample of butyl butyrate? Okay. Now, one thing that I'd like to say is, considering that you're presented with the molar mass, clearly this question could have gone in a different direction. It could have asked you for the empirical formula. It could have asked you for the molecular formula. But this is just asking what is the mass of O. Okay, so we've got 6.10 grams of CO2. What we need to do with that is we need to figure out the mass of carbon that was actually used. Now, when you look at that 6.10 grams, that might be a little bit confusing because you might be saying, well, we had 2.5 grams and now we've made 6 grams. Well, yes and no. Keep in mind that we're burning this hydrocarbon, so what we're adding to this is excess O2. So anything that, like the fact that the mass went up, or sorry, there's more CO2 produced than there was butyl butyrate originally, should not be a concern to you at all. Okay, so what I'm going to do is I'm going to convert this CO2 into mass of carbon present. So that's 44 grams of CO2 is 1 mole of CO2. 1 mole of CO2 has 1 mole of carbon. 1 mole of carbon has a mass of 12 grams of carbon. So I'll plug all that in, multiply it across the top, 6.1 times 12, and divide that by 44, and that gets me, I'm going to call that 1.67 grams of carbon. Okay, now is that a number that looks about right? It does to me, because 1.67 grams is less than that 2.50 grams. And so comparing this number right here to this number right here is a fair thing to do. Okay, next up is 2.50 grams of H2O. Okay, so 2.50 grams of H2O. Water has a molar mass of 18 grams. H2O is 1 mole. One mole of H2O has 2 moles of hydrogen. 1 mole of hydrogen has a mass of 1 gram of hydrogen. So 2.5 times 2, I'm going to divide that by 18, and I'm going to get 0.28. Okay, so that's the mass of hydrogen present. So my question was asking, what's the mass of oxygen? So all that I'm going to do is I'm going to take 2.5, and I'm going to subtract 1.67. Then I'm going to subtract 0.28, and that's going to get me 0.55 grams of oxygen is present in a sample, in this particular sample of butyl butyrate. All right, I hope this is helpful, and that's actually the end of chapter number 3. Definitely get after this homework. It's a little bit challenging and a little bit long, but there's a lot to this. All right, well, have a good one.